Alright, this is NCCER Electrical 4, Module 3, Module 26403-20, Standby Emergency Systems. Alright, so Section 1, Standby and Emergency Systems. They're going to talk about different types of generators and stuff like that, and how they are hooked up and what they power and what they have to power and how fast they have to come on, and just the different requirements that are based on that stuff. They talk in the trade terms like the armature, exciter, synchronous generator. All those are talking about just the way of generating some type of voltage, because some stuff is backed up with AC power, some stuff is backed up with DC power or DC voltage, AC voltage. But my first highlight on page 1 is on the right hand side of the page, right after those bullet points. The first paragraph is highlighted. In the event of a failure of the normal power supply, emergency lighting, emergency power, or both must be available within the time required for the application, but not to exceed 10 seconds. So it has to happen within 10 seconds for these standby emergency systems. Immediate next paragraph, first sentence is highlighted, separate highlight. Legally required standby systems are defined by NEC Article 701 as those systems required and classified as such by municipal, state, federal, and other codes, or by government agency having jurisdiction. So these are the code book says what has to have these standby electrical systems, whether that be a hospital, something that has to come back on, and how fast they have to come back on, and what all devices have to come back on, because not everything has to come back on immediately, or not everything has to come back on at all, but stuff like the lighting and emergency systems and power and stuff like that. That's the stuff that must come back on. Moving on to page 2, system components. 111 engine-driven generator sets. So you got engine-driven generators. Most of the time for these big backup systems, these are big giant diesel engines. Like you can see the typical engine generator set. You see that big, looks like a big cat. It says cat at the bottom. Generator. So the front, the left-hand side of that, like you go from like radiator, fan, engine, generator, and then controls all the way towards the right-hand side. 111, the engine-driven generator sets. Second paragraph, second and third sentence, you're going to have, I got 4 questions that come out of this second paragraph of 111. So quite a bit of stuff. So second sentence says the AC generator consists of a rotor, shown in figure 2, which is for y'all, that's what's on the board or on your page 4. Also called an armature. So that's what actually moves. And a stator. Stator is the non-movable part that contains the magnets with the shaft of the rotor bearings being driven by the engine. When the engine is running, it turns the rotor, which carries the generator field windings. You need to know that the rotor carries the generator field windings. Out to the side of that highlight, I wrote no transfer switch. There's not a transfer switch in this setup. Next sentence is highlighted. These field windings are energized or excited by a DC source called the exciter. So field windings are energized by the exciter, which is connected to the positive and negative ends of the field windings. Separate highlight. Last highlight. The immediate next sentence. The generator is constructed such that the lines of force on the magnetic fields cuts perpendicularly across the stator windings when the engine turns the rotor, causing a voltage to be induced into the stator windings. So, looking up on the board, this turns. The magnets on the outside cause the induction of current in the windings inside the stator. The rotor moves, stator does not move. The moving of the rotor or the armature causes voltage to be induced into the stator windings. Stator does not move, rotor or armature on the inside moves. Up above for that last highlight, I wrote up at the top and wrote an arrow down to where the highlight is. I wrote the stator is the stationary part of the motor generator. What did I just say? You can see figure 1, like it's going back a little bit, like you can have your generator set, like your normal, going back to this picture, you can have up here at the top, you can have, if you guys can see that, you can have the utility transformer. I'm looking at figure 1 in your book. That's your normal service. So like you have your breaker that comes in, overcurrent devices, more breakers. This goes to non-emergency loads. So this all, if power goes out, these do not come back on. This breaker or overcurrent device over here, whether it's a fuse or a breaker, comes down and feeds this distribution panel, which feeds all of everything that has to be on the emergency loads. So power gets shut off by the utility. So in our area, something that happens, Entergy shuts off power. This generator set has to come back on within 10 seconds, and then powers up everything that has to be on the emergency side. So you can see your transfer switches right here, line coming down from your normal distribution panel. The transfer switch is just going to switch from normal power to emergency power. It's just a simple one-line diagram of an emergency set. Flip it over to page 4, 112. Generator selection and consideration and sizing. First paragraph down towards the bottom left of page 4. It's that last 2 full sentences down there. Problems of fuel storage can be a deciding factor in the selection and types of generators used. If natural gas is used, its BTU heating content must be greater than 1,000 BTUs per cubic foot, or 37 megajoules. I never heard of megajoule per cubic meter. That's just saying there might not be enough energy inside of natural gas in order to turn these big generators. That's why most of the time, like it says it right there below, diesel powered generators are widely used because they require less maintenance and have a longer life. Whereas natural gas generators burn a lot cleaner. Diesel generators are a lot easier to maintain because you can go start them up. They're pretty rugged. If you're not going to run a generator, like you can put, a regular truck can get 400, 500, 600,000 miles off of a diesel engine. So we're not, like, it's not even, producing power is not even as hard as it's a lot better on a diesel engine than even us driving them around. And these are massive diesel engines. This next paragraph on the right hand side of page 4, I've got the second to last sentence in that paragraph highlighted. The most common generator set arrangement has a mounted radiator and an engine-driven fan to cool the coolant and ventilate the generator room. So you can see like that picture that was on, you can't really see it in the picture on page 5, but on page 2, that typical engine generator set, that is a massive fan to cool that engine, cool the coolant for the generator, cool the coolant for the engine, but it also blows out a lot of times in the places that I've worked, you can see on page 5, you can see those big exhaust vents on all that stuff, and that is exhausting. Like you couldn't have like the carbon monoxide inside that room. Like they say the fans blow stuff around, but really that stuff is the carbon monoxide and stuff off of the diesel fumes is being exhausted out of those rooms. That is a super clean generator room. Ones I've been a part of at Goodyear and Nucor did not look like that. They weren't bad, but that is a clean room compared to where I've been for emergency backup power. Page 5, the bottom left of page 5, I've got the last sentence down there in the bottom left highlighted. Once the starting and running loads have been determined, it is common to add a margin factor of up to 25% for future expansion or to select a generator set of the next largest standard rating. So that's just saying don't size your generator to what exactly you have. Make that thing bigger, buy the next bigger size. Usually, like even for your houses and stuff, everybody knows like you can get down to like 2,000 watt generator, then it bumps up to 4, then 5, then 6,500, 8,000, 10,000 watt generators. So they usually come in specific sets, so they're just saying buy the next size. On the right hand side of page 5, last paragraph before 113, the last sentence is highlighted. Applications with the following types of loads and similar devices may also require that the generator be oversized. If you have fire pumps, I got fire pumps highlighted. I know at Goodyear, the building that I worked at Goodyear was 52 acres under roof. Massive building. They had to have fire pump stations at all 4 sides of the building. And I would have to walk around to each one of them, start them up, and make sure, like they had their own like backup generators in those pump houses. So they didn't necessarily have to be oversized, but if you had a building that had to have fire pumps, you might have to oversize it so that those fire pumps are going to take a lot of power to get that water moving and stuff like that. But just know that's one version, or they've got UPSs, variable frequency drives, battery charging rectifiers. So if you're charging batteries of some type that have to stay on, that are emergency power, like those are just different reasons why your generator might need to be oversized. Flipping over to 120 transfer switches. So, like I said before, transfer switch is essentially all it's going to do is switch you from normal power to emergency power. I don't have anything highlighted on page 6, but they do go through the functions of a transfer switch, and those 6 bullet points on page 6 wouldn't be a bad idea reading through that while you're reading through this chapter. On page 7, my first highlight's all the way in the bottom left of page 7, first sentence of that paragraph that starts down there. A third time delay, usually adjustable from 0 to 10 minutes, is provided to allow cool down for generator set engine cooldown. Is provided to allow for generator set engine cooldown. Generator set engine cooldown. So that's just saying once you switch back to normal power, that generator might continue to run for a little bit of time, and that's going to give that time that coolant time to cool down through the because of the fan, and the engine's going to cool down because it's going to be running at no load. So that engine's just going to cool down rather than just shutting it down right away. The last sentence of that paragraph in the top right of page 7, note that running an unloaded engine for more than 10 minutes is not recommended because it causes deterioration in engine performance. So you can set that time delay from 0 to 10 minutes, but don't go above 10 minutes for running that engine. It'll cool off faster than the 10 minutes. Transfer switch configurations and sizing, 122, flipping over to page 8. That last paragraph before 123. First sentence is highlighted. The sizing of transfer switches is based on the calculated continuous current. So remember from previous electrical classes, anytime you see continuous, you have to think like it's usually calculated at 125%. In a manner similar to sizing the circuit conductors. So same thing. You're sizing this stuff by probably up by 125% because it's considered continuous. Because if you run this stuff, you might run it for 10 minutes. You might run it for 5 days. Southeast Louisiana, everybody has been without power and realizes probably everybody's run on generators and stuff like that. Like everybody knows, like we can get power back quick or we can get power back next week. So they have to consider this stuff continuous loads because they don't know how long it's going to be. You got 2 questions in section 2 review, so make sure to hit those, but I'm going to continue on to section 2, storage batteries and UPS systems. Storage batteries and UPS systems. UPS system is pretty much just a battery. It's a backup battery. or a series batteries. Storage batteries, 210. I've got the first, just one sentence, first sentence and 210 highlighted. Section, NEC section 701.12c specifies that a storage battery of suitable rating and capacity is required to supply and maintain at least 87.5% of the system voltage for the total load of circuits supplying legally required standby power for a period of at least 1.5 hours. When I was going through this chapter, they hit those numbers pretty hard. Like you need to know that 87.5% of the system voltage, and then it needs to be able to run it for at least 1.5 hours. So keep those in mind, the 87.5% and the 1.5 hour required run time. They talk about different types of batteries. You got your lead acid batteries and your nickel cadmium batteries. Nothing highlighted in those, just different ways of moving those electrons around and different storage abilities at the negative terminal for different types of batteries. Battery maintenance, 220, battery maintenance overview. Sentence that splits the columns on page 11 in 221. Overcharging a lead acid battery will destroy the positive plate, evident by a characteristic of dark sediment at the bottom of the cell jar. So don't want to overcharge these batteries. Usually this stuff is like 12 volts or more. Usually like an alternator or something like that is charging them all up to 14 volts, but you're not wanting to go above that. You also have different types of chargers. Usually a trickle charger, like putting high amperage on a battery is not good. Like adaptive charging, not running a battery will last a lot longer if you don't run it all the way up to full charge, and if you don't run it all the way down to all the way completely dead. If you can charge and keep a battery somewhere between like 20 and 80%, that battery will last a lot longer. That's become evident as more and more electric cars have come out. Last sentence on the page, continuing on the next page, is highlighted. The nominal open current voltage of a lead acid cell is 2 volts, and of a nickel cadmium cell is 1.3 volts, but the charging voltage is higher. So you see they have lead acid battery is 2 volts, and a nickel cadmium cell is 1.3. Have those two, you have a question based on those two. Page 12. That next paragraph on page 12, or first full paragraph, I've got, I guess it's the second to last sentence highlighted. It's kind of right in the middle. The specific gravity of water is 1, whereas the specific gravity of sulfuric acid is near 1.15 when a battery is discharged, and 1.28 when it is near full charge. So, specific gravity of sulfuric acid is going to be higher than water, but it changes based on charge. So 1.15 when it's discharged, 1.28 whenever it's near a full charge. Paragraph in the bottom left of page 12, first sentence is highlighted. The method of determining battery capacity is by performing a load test. Load test. To measure the amount of power a fully charged battery is capable of delivering over a specific period of time. Specific time period. But they do a load test to determine battery capacity. Simple enough. You can see, like as you're going through all these pictures and stuff like that, they have different batteries, and they're showing the insides of them. Lead acid battery construction up in the top of page 12. They can show the different plates and stuff inside of those. The lifting brackets, these batteries are stupid heavy. Batteries are heavy. These big batteries are crazy. Like this is picking stuff up with a forklift type battery, not lugging that thing around by hand. And then you can see the batteries on page 13. Just looking at those, you can kind of tell that they are, it looks like they're wired in series. Yeah, wired in series because that's a high amperage modular battery. So that you can tell by just looking at the plates and stuff, or the connecting rods connecting all the different terminals together. If it's going from blue to red, I would assume that's negative to positive, which would mean that that's wired in series, which means that is adding high current batteries or high amperage batteries. But just pay attention whenever you're going through the book, taking a look at pictures and stuff like that. They go through the battery maintenance guidelines. You should like save tools because this stuff has acid in it and whatnot. Like you just want to make sure that you're safe when you're doing this. Page 14 goes through like your monthly checks, your monthly checks. For tasks, they do monthly checks. On the right-hand side of the page, I have, before the second set of bullet points, I've got a typical maintenance interval for each task is shown. And then if you go on to page 15, I go under annual checks, and you need to have the third bullet point under annual checks highlighted. Intercell connection resistance for vented lead acid batteries. So you need to make sure that your connections between batteries has a low resistance. You don't want any kind of like corrosion or anything like that. A buildup of that stuff causes higher resistance, which is pretty much just stealing away from your capacity. Battery and battery charger operation. Right-hand side of page 15, the last two sentences of 223 are highlighted. Also note that a battery's charger output must be derated for altitude when it's installed at locations above 3,300 feet, and for temperatures when the ambient temperature exceeds 122 degrees Fahrenheit. Luckily for us, it's not, please help it not get above 122 degrees Fahrenheit, and we are definitely not at 3,300 feet above sea level. But those are the two numbers that, I have the last sentence highlighted too. The battery charger manufacturer can provide these derating factors. If you stay in this area, probably not going to have to worry about those. But have those two in your mind. 3,300 feet above sea level, and then if you're over 122 degrees Fahrenheit. Uninterruptible power supply systems. So page 16, you've got the double conversion UPS system. So a UPS system is it's a battery backup system. And it's usually for servers or computers or something like that, so that whenever sometimes power will blip, and these batteries will back that up to where you won't even see that blip in power, and then sometimes it has to run for a little while. But they're just battery backups for 231. Right before the bullet points on page 16, or the first set of bullet points, I've got that sentence highlighted. The double conversion system has several advantages. Has excellent frequency, I've got all the bullet points highlighted. Excellent frequency stability, high degree of isolation from various incoming line voltages and frequency. Zero transfer time possible, which that's where you won't see the blip or anything like that. Quiet operation can provide a sinusoidal output waveform with low distortion. So that just means that it can provide clean power, clean AC power. The next sentence is a separate highlight. In low power UPS applications, 0.1 kilovolt amps to 20 kVA, the double conversion UPS can have some of the following disadvantages. I just have the lower efficiency. So at these levels, these UPS systems can have a lower efficiency. Going on to 232, the single conversion UPS system, I've got the second sentence highlighted. The normal AC power is supplied directly to the critical loads through a series inductor or transformer. The normal AC power is supplied directly to the critical loads through a series inductor or transformer. That is on page 19. You've got figure 11. And I've got the figure 11 is highlighted, and you're gonna need to see where the AC input goes. So your alternating current goes to the series inductor or transformer, and it also goes to the battery charger. So you're just going to need to know that figure for one of the module review questions. You got the section review questions at the bottom of or on page 19, and then I'm going to continue on through section 3. Section 3, NEC requirements for emergency systems. First paragraph on page 20, second sentence. In general, NEC Article 700 deals with emergency systems. Article 700. Next section, 310, legally required standby systems. 310. First sentence is highlighted. NEC Article 701 or 701 covers installation requirements of legally required standby electrical systems. 701 is for legally required standby electrical systems. Paragraph, skip that little short one sentence paragraph, and the whole next paragraph is highlighted. You have two different questions come out of this one paragraph. Just key in on whenever I'm keying in on certain sentences. In general, legally required standby systems are typically installed to serve loads such as heating and refrigeration systems, communication systems, ventilation and smoke removal systems, sewage disposal and lighting systems, and industrial processes that, when stopped during any interruption of normal electricity supply, could create hazards or hamper rescue of firefighting operations. So you're going to have all different types of stuff that has to stay on emergency power. Just going through one example of something that probably nobody has thought about taking this class. But whenever I was at the steel mill, we made the big coils of steel, and we would galvanize them. So one of the last processes in the whole plant was if the customer wanted to galvanize it, we galvanized it. When you galvanize something, you're just putting a thin layer of zinc on the outside, and that provides a corrosion resistant effect to the metal. How you get that is you have a big giant vat of molten zinc. So our zinc pot at the steel mill where I worked at was probably about the size of this room. I know not everybody's gonna be able to see this room, but this room pretty big, probably 20 by 20, filled with molten zinc. We would have downturns where the whole plant would shut down, and we'd replace a lot of parts that need to be replaced. Big capital projects would be done. This would be like a week or week and a half long, 10-day process, and stuff would shut down. Sometimes they would be changing out a big transformer in the yard. They'd have to shut off power, stuff like that. We had a backup. This longer story shorter. This zinc pot had inductors that, like, just longer rods that were down in it that just heated up and kept that zinc molten, kept it moving, kept it molten. And those were connected to emergency power, because if we shut down power to those inductors, that molten zinc would solidify, and in order to get it, you can't just heat up a 20 by 20 room of zinc. You would burn up the inductors trying to heat up that much zinc. It would never get going. It'd just burn it up. Something happened once. They shut down power. Generators came on. I assume I wasn't there when this happened, but the generators came on, and people just went on about their business because generators were on, power was being supplied, stuff like that. Generators were not being checked. There was a guy walking past the zinc pot, and usually whenever there's like a little piece of slag or something like that, or a little piece of zinc, they would just kick it off in the zinc pot for it to melt, and that's just where stuff went. Kicked it off in there, and it bounced across the top. That zinc had solidified. People started crapping their pants, ran out to the generator room. The engines had, at least the engine that was running, had kind of exploded. There was oil, not exploded, but blew a piston or something like that. Oil was everywhere. There was like 3 inches of oil in the bottom of the floor, stuff like that. Engine had shut off. There was no, so big no-no. But all that to say, there's stuff that has to be powered by emergency systems, and it has to be checked that maybe you might not normally think of, and that's just what that highlight was talking about. Moving on. Last paragraph on page 20, first sentence is highlighted. Current must be supplied to legally required standby systems so that in the event of a normal power failure, legally required standby power will be available within the time required for the application, but not to exceed 60 seconds. So these systems has to come on within 60 seconds. That's what you want to key in on for these legally required standby systems. Healthcare facilities 320. So just going from the chat module 2 into this, we know that a lot of the plugs and stuff are going to be on different standby systems, whether they're tagged green or red or the different colors and stuff like that. We know that the healthcare facilities have to have backup power. 320, the second sentence through moving on to the next page, just barely is highlighted. Essential electrical systems for hospitals must comprise, key in on 3 separate branches capable of supplying a limited amount of lighting and power service that is considered essential for life safety and effective hospital operation during the time of the normal electrical service is interrupted. So, you have to have 3 separate branches capable of supplying a limited amount of power. Page 22, next paragraph, first sentence is highlighted. Each patient bed location must be supplied by at least 2 branch circuits, 1 or more from the critical branch and 1 or more from circuits from the normal electrical system. So one is going to definitely have backup power, and 1 or more is going to have backup power, and 1 or more is going to be just from the normal electrical supply. And then, like you guys have already done the healthcare facility, so you know that there's got to be more than just 2 plugs. So there's got to be, like, some beds have to have 8. Operating rooms have to have 36, I think it was. But you just need to know that a lot of those have to be supplied through 2 different places. On the right-hand side of page 22, right before those bullet points, the entire paragraph is highlighted before the bullet points. The life safety and critical branches of the essential electrical system must be kept entirely independent of all other wiring and equipment and must not enter the same raceways. Can't even be in the same pipe, boxes, or cabinets with each other or other wiring, except as follows. Can be in the same transfer switch. Can be in the same exit or emergency lighting fixtures when supplied from 2 sources. Can be in the same common junction box attached to exit or emergency lighting fixtures supplied from 2 sources. So, don't have to have 2 sets of emergency lights, but all the plugs and everything else has to be. It's like a hospital or nursing home or any kind of critical care facility has to be wired twice. A lot of, so you think about these contractors doing these hospitals and stuff like that, you're kind of getting two paychecks for this. Like, you're having to wire it once and you're having to wire it again. Big time money for wiring up hospitals and stuff. Next page, page 23. The sentence before the first set of bullet points is highlighted. The life safety branch must supply power for the following. I keyed in hard on the first bullet point, lighting required for corridors. You gotta have lighting. Passageways, stairways, and landings at all exit doors. A lot of times these emergency lights, like this whole room, I got 9 lights in here. Sometimes the emergency lights is just enough for like walkway lighting, so it might be like every 4th light has to come on in the emergency, just enough to be able to walk down corridors and stuff. But you also have to have exit signs, alarm and alerting systems, communication systems, generator set accessories, elevators, automatic doors. All that stuff has to be on emergency power, especially in the hospital. You think about, like, why on earth would you have to have an elevator on emergency power? You not try to get somebody down the stairs in a wheelchair that has 0 help at all. Elevators have to be on emergency systems. Page 24, places of assembly. 330. I've got the first sentence highlighted. NEC Article 518 covers assembly occupancies. That is all buildings or portions of buildings or structures designed for intended for assembly of 100 or more persons. Such facilities include assemblies halls, restaurants, dance halls, courtrooms, auditorium, churches, and similar locations. So these places of assembly include churches. Emergency lighting, 340. Sentence before the bullet points is highlighted. In general, the following items must be fed from an emergency circuit in public buildings. I have all the bullet points highlighted. All exit signage, all exit lights, sufficient emergency white lights, fire alarm system, life safety system, sprinkler system, water pumps. Out to the side of that, I wrote no computer equipment. Computer equipment is not part of the emergency circuit in public buildings. You don't have to have computers come back on. Page 25, moving on to 341, the battery-powered emergency lighting. First full paragraph on page 25, first two sentences are highlighted. Specific requirements for emergency lighting are defined in NEC section 700.15 through 700.26. The required backup time for batteries for emergency lighting is an hour and a half, which is 90 minutes, although some systems may be designed to have a longer backup time. So if you got batteries that are turning on your emergency lights, they have to last for at least an hour and a half. So all these little lights, like up here on the board, have little batteries in them. They should be able to stay on for an hour and a half. So these batteries, like a lot of times you got to replace these batteries and stuff like that, like going through and pushing the little test light, making sure they work. That's good. But you have a power outage and stuff like that, and they deplete these batteries. Like a lot of times, like I've had to go back through and replace batteries. That is all my highlights for this section. So you got section 3 review on page 26, module review on starting on page 27, and then you got a supplemental exercise questions on page 29, and your practice test. I think you've got 15 practice test questions to do for this chapter.